Hi, I'm Bill Lionheart. This is the next in our series of tutorials on inverse problems and tomography reconstruction. So I'm just going to look a little bit about how the singular values and the singular vectors of the 2D radon transform change when we limit the angle of the data. As before, this is run as a Matlab live script tutorial coming up on the screen. Okay, so I'll put a link so you can find these Matlab live scripts in the notes underneath this video. We're going to use AIRTools to make our matrix. Here's the link, download that. And we're going to use some scripts that are associated with our book, and the reference book will be at the end. So FA18. That means Fundamentals of Algorithms 18. Nothing to do with aircraft, but may have the same name. Okay, so we set up a parallel beam tomography problem. We're going to take a 50 by 50 pixel grid, so n equals 50. We're going to take initially angles in steps of 2 degrees and 75 rays per projection. So we set that up with parallel beam tomo from AIRTools, and it gives us the matrix A as well as the sample image B and what the unknown vector x should be. So that's x as a sample image and B is the sinogram data. A is a sparse matrix. Okay, so I can execute each of these sections by highlighting it and doing run section. I've got them already ran just for speed. XC is the vector of pixels just on the circular disk inside the unit square. So we're just reconstructing pixels that lie in the disk, and that matters a little bit if you want to look at the singular functions, because they have a certain symmetry property. And so we also restrict the matrix to those pixels that lie inside the disk. Okay, so SS is the SVD. I had to do full of the matrix. The circular one was a little bit smaller than 50 by 50. I'm going to plot the log singular values. Now, I've divided by the first singular value, which is the operator norm of the matrix A. And that's really to make it easier to compare between different matrices that might have slightly different norms. The log scale, log scale, means that a straight line corresponds to a power. So we see a negative power of sigma n as a function of n. And so until it falls off sharply, we see that it's going down exponentially. But you should never really trust something just based on one discretization if you're trying to understand something more general. And there's a pattern here that it looks like they go down in steps of, well, it looks like 2, I'm not sure on the log scale, but groups of singular values are the same, but generally the trend is there's this power law, and then they fall off, and when they're very small, the singular value decomposition struggles numerically to get accurate singular values, but possibly as a result of the errors in floating point computations tends to make a nice round curve where it should just fall off steeply where the rank actually decreases. Okay, so we should ask if that's any different if we use more grid points. And so if we do 100 by 100 pixels, but again, knock off the ones outside the circle, then rather reassuringly, we get exactly the same pattern, but of course it falls off later because the actual rank of the matrix is bigger. I increased P, I increased the thetas to be in 1 degree steps, so I've increased the resolution in the sinogram space. I've also increased the resolution in the pixel space. So that's reassuring, and if you did it varying discretization a bit more, maybe hopefully you'll find that it follows this pattern, which should agree with the analytical calculation, or tend towards the analytical calculation that you'll find in our book that we've referenced below. Now, if we restrict the data, for example, if we restrict the size of the detector so it can't see a full width projection of the object, so if the detector is narrower than the object, sometimes happens, or if we're not able to rotate the object all the way around, perhaps there's some limitation of our apparatus and the geometry. So these are actually both quite common. I suppose you could just slice off bits of the matrix, slice off columns of the matrix, and it would make a limited data problem. But just as an easy, quick thing, you can try other things. If we slice off some angles, so I can do that kind of without recalculating by, we did it in 1 degree steps, and each projection still has P 150 measurements or sensors in each projection. And so if I take the first 30p columns of the matrix, then I've limited the angle to 1 to 30 degrees, so quite a small range of angles. And so we expect it to be more ill-conditioned. So we plot the normalized singular values. And so remember, we plotted it on a log-log scale before. It's not slightly out of sync. Okay, so limited angle data on the log-log scale. And it's not sort of really clear what's going on the log scale, whether, I mean, because I should have maybe cut off the tail to look at it more carefully, right? So I should have maybe plotted from there to 1,000 or something. But we can also do it on a log linear scale. Now, the log linear scale is designed to reveal if it's falling off exponentially or faster than exponential. So a semi-log y in Matlab does that, so it's a log of the singular values, but the linear scale for the number of the singular value. And so in this case, what we see is something more or less straight on the log linear scale, which means that the decay of the singular values is in fact exponential, possibly slightly faster than exponential, because it's falling off there. So as soon as we've limited the data, we see something that's what we'd call severely ill-posed, like the heat equation that we saw in 1D was severely ill-posed, whereas the deriv 2, remember from regularization tools, that was mildly ill-posed. And so as soon as we start limiting the data, we tend to get severely ill-posed problem. There's some more understanding of that in the theory, in the chapter on unlimited data in our book. But also there's an underlying phenomena in a lot of inverse problems that limited data problems are closely related to analytic continuation. And in the radon transform, you see that the Fourier slice theorem converts the radon transform to a Fourier transform. And so if you have the Fourier transform of a function that's compactly supported, in this case on the disk, it's zero outside the disk, its Fourier transform is analytic. So that means you can do analytic continuation, you know, at least as far as the Taylor series converges, you can work out the Taylor series, and if you know the function on an open set, you can extend it. But the point is, calculating all the terms in Taylor series, we think of that as involving very high derivatives. Obviously, that's a very unstable thing to do. And so analytic continuation, as you'd expect, is very unstable. So often severely opposed inverse problems are similar to analytic continuations. Also, sometimes the underlying phenomena is that they're a bit like the backward heat equation. Anyway, so that's severely opposed, and I invite you to try reconstructing that with the regularization methods in the previous tutorial. So what we'd expect to see is that the choice of regularization will have a much bigger effect on the image that you get. So if you use Tikhonov or generalized Tikhonov or total variation, it'll depend on the choice of regularization, and also depend a lot more on the regularization parameter than mildly opposed problems. So I invite you to try that, making some right-hand sides for, you can make up the test X as well in some kind of simple pattern. Add noise, as we did in the last tutorial, using rand-n typically, which makes Gaussian random noise, and see what happens with severely opposed problems like this. Just going back to the full problem, let's look at the singular vectors, or, so these are approximations to singular functions in the, I don't think I've run this one, approximations to singular functions in the operator case. So in other words, if you have absolutely all possible data for every possible angle and infinitely many detectors, then the result is an operator where you recover a function instead of a vector. So yeah, we've got an error message. Let me just check what it is, because, well, you can get an error message. Also, the lights went off. Quite coincidentally, it's on a timer. Unrecognized variable V. Okay, because I didn't run that part, right? So this one, SVD, a full AC, U, SV, there are the matrices that, if you use them either side of AC, will diagonalize it to get the matrix S. And I'm going to have to run that a bit. You can try on your own computer how big an SVD problem you can actually solve. Look, there's a little thing whirring there, because obviously it's a little bit more demanding with this big matrix and working out all the singular values and singular vectors. The V vectors are going to be the image vectors, so it's AV equals US, and the U's will be a basis for the space of sinograms that spans all the sinograms you can get from doing your radon transform with this discretization. Oh, it must have worked, because now my V's come up as a matrix. There we go. Rather a huge, but nevertheless orthogonal matrix. And now I should be able to run this section. You can put extra section boundaries in if, typically you don't want to rerun all the code. So sections are kind of nice when it takes a while to get the answer. And we're still trying to plot these things. There we go. I'm using tiled layout, which is the new the new Matlab thing for subfigure. So these are the left singular functions, and these are the right singular functions. So the right singular functions are the basis of images, and if you look in our book, it explains why these are Zernike disk functions. So they're quite nice series of functions that was probably first used in optics problems for designing lenses and such. So these are the components of the images on the disk, that in order of how easy they are to find. And of course, it looks a lot better on the disk. If you do it on the full square, then it's not rotation symmetric, and you don't get anything quite as nice. And if you do limited angle data, of course, you'll find that everything is also biased towards certain angles. So it's worth a try. The singular functions on the data side, these are the things you can make valid sinograms out of. Each one corresponds to one of the right singular vectors, and because the singular values are decaying, the amount of each of these that come out is decreasing. So when you add error into it, and especially notice they do tend to be somehow higher frequency, there's at least part of it is a Fourier basis. The later ones, the higher frequencies are harder to find, and that's true in the image ones as well, except there's a kind of pattern where it goes it's circularly symmetric, and so it's twofold symmetry, and so on. There's a pattern to them that in a way I probably should have plotted them out in a triangle, which you'll see the way we did it in the book. Okay, so I invite you to have a play with that, see what the singular values and singular vectors look like for different limited data problems. The book I referred to is Hansen, Jorgensen, Lionheart, and our mates, right? So we're the editors, and we have some other very nice contributors to specific chapters. And the website for the book is there, including the link to a little bit of code. There'll be some more code later, I suppose, appears there. AIRTools is referenced here. If you use AIRTools in a publication, please refer to that paper. But if you just want to download it and use it, you can just get the zip file from the Git repository that I listed at the beginning. Okay, so probably the next in this series, the one to watch is the total variation tomography one, where we just try a bit of total variation TV regularization for this 2D tomography problem. Okay, that's all for this quick one. Hope you enjoyed. Bye.